We continue review in algebra. Question 19. Describe all the solution of x equal to b. So this matrix A, vector B. So we just multiply them together with the vector x and then solve for x. So A times vector x equal to vector B so that the matrix A now times x equal to the matrix B right. So because this one has 3 columns, we require 3 variables. So each one will correspond to 1 column. Right. Now with that we just write the romantic matrix for this system of equation 2, -5 and 3, -1, -2, 6 and -5, 6, -4, 7 and 0, 13. Right. We just need to do the reduced row echelon form for that. Three row, 4 columns. Okay. Right. 2, -5, 3, -2, 6, -5. Wait. So look at this. -1, -2, 6, -5, 6, -4, 7, 0, and 13. Right. And hit enter. So that's what we get. Okay, -13. Because otherwise this is no solution. Right, one more time. Alright, so this one, infinitely many solutions, because we do have a free variable here. Right. Yeah, let's change this to fraction. Right. So if we write x1, x2, and x3, we have the pivot on x1 and x2. Therefore, those are the basic variable. The free variable would be x3 because there's no pivot on this column. So we say x3 is free variable. how we say x3 be any number or be a free variable. Right. For the first equation, we have x1 minus 7 over 2, x3 equal to 12. And so for that, we have x1 equal to, let's say 7 half, x3 plus 12. And then for the second row, we have x2 minus 2 x3 equal to 5. Solving for x2, we have 2 x3 plus 5. Right. Now with that, we can write the solution as x1, x2, x3 equal to x1 is this 7 half x3 plus 12, and then 2x3 plus 5, and then x3 just x3. So now we split all of this, have x3, we factor out. We're going to have 7 half, 2, and 1. All of them have x3. The other one doesn't have anything, just constant. 12, 5, and then 0. Right. So we write the solution and factor out x3. We have this. So the conclusion here is that we say this is going to be a line because this has one parameter, so one-dimensional object. It has to be a line and in three-dimensional space. And this line will go through this point and it will be in that direction. So when x3 equal to 0, we go to this point, and that is the direction of the line. So bottom line is, we just describe this. It is a line because it only has one parameter, so one-dimensional object, and in three-dimensional space. Right. So that's what we have. Right. Now we have this. We have three vectors determined if the set of vectors are linearly independent. So there are a couple of ways to do this. If we use definition, or in chapter 3, we put this in the matrix and find determinant. If determinant is not equal to 0, the set of the vectors are linearly independent. What we do here is we just use the definition. Definition of linearly independent is that if we have a trivial solution where we have the homogeneous system, we only have trivial solution. Right, so in that case, what I will write is, if we have the system, let's say x1 v1 plus x2 v2 plus x3 v3 equal to 0, it is linearly independent if this one has only trivial solution. So we're going to check that. So what we're going to do here is we're going to put 3 columns. and each column we have a number x1, x2, and x3. 0 will be just a zero vector. Now we're going to put this in the matrix matrix and do reduce row echelon form. So the matrix matrix usually we don't even need to put the last row of 0. We'll talk about that in a minute. If the last row is last column is 0, doesn't matter what the row operation we do, we end up with the last column is 0, remain the same. Right, so now put the matrix 3 row 4 columns, so that's good. 1, -3, 2, and 0, -3, 8, -2, 8, 5, and -6. So let's check. Right, so we end up with that. So for x1, x2, and x3, we have the pivot on every row, or no free variable here. Right, I should say there's no free variable. So we have a pivot on every column. So in this case we have only trivial solution, right? x1 equal to 0, x2 equal to 0, x3 equal to 0. So what we have is we only have, I would say, the system only has trivial solution. x1 equal to 0, x2 equal to 0, and x3 equal to 0. So the vectors are linearly independent. So that's one way to do that. Like I said, there's another way we look at this. But another way to do this is use this terminal in chapter 3. So second matrix, right on the first one is terminal. And 3 by 3. If the terminal is not equal to 0, then the system is linearly independent. So here we should not expect, we should expect the determinant to be something else than 0. So that's not equal to 0. So they are linearly independent. Right. Also, when we do this, we really don't need to do the last column of 0, because whenever we do, the last column still remains 0. So we try to focus on the left side of the matrix matrix. If we have no free variable, so there's a unique solution. If there's free variable, so the solution is not unique. So that's what we have. Right. Next, let A and U be that. Define the transformation from R3 to R2. Defined by by this transformation, find T of U, the image under transformation of this one. Pretty much very straightforward. So we go from R3 to R2, but the transformation represented by T of X equal to H of X. Now if we have U instead of X, so T of U equal to A of U. A of U. Right. So of course we can use the calculator to do this, but if we multiply by hand, of course in the next in chapter 2 we do learn a way to multiply the matrices together, but this time we use the vector version. So that each column multiplied by a vector, so each component of the vector will attach to one of the column. So 8 will go with the first column, 2 with the second column, and -3 with the third column. So that gives us -8 and 24. 16 and 8, 3 and -6, 1 add all of them up, 8, 3, 11, A minus 6, 2, so that's 26. So we have 11 and 26. Right? So T is a transformation that transforms this vector U in R3 to this vector in R2. So that's all we do, really. Right, next. We have a transformation from R3 to R3. Now, if possible, find a vector X whose image under T is B. Right? So this time we have inverse problem. We have Tx equal to Ax. And this time we want that to be B. So pretty much we show the system A times X equal to B. Right, this is A. So we will write A is 1, -3, 0, -4, 0, 2, 1, -5, and 4 times X. This is in R3 equal to also a vector in R3 which is B. Yeah. Now we just solve for X. That will be easy. Second matrix. Reduce row echelon form. So 1, -3, and 18, -4, 0, and 2, -10, 1, -5, 4, and 32. Right, let's check. Right, so we end up with that. So let's find the vector X whose image under T is B. So yeah, so that's what we have. So just say reduce row echelon form. Of course, we know that we can put this in the augmented matrix easily, but just say 1 0 0 0 1 0 0 0 1. Yeah, so we can put that in the augmented matrix easily. And when we do this, again, x1, x2, x3 for each column. And the pivot. So we have x1, x2, x3 equal to 3, -5, and 1. So this is what we call the pre-image. It will transform into the vector B under this transformation. Right, next, the column of the identity matrix of order 3 is 1 0 0 0 1 0 0 0 1. So in column E1, E2, E3. Suppose T is linear transformation from R3 to R2 such that it maps the E1, E2, E3 into this. Find the formula for the image of an arbitrary X. This will be vector X in R3. So that will be very easy. So we have the transformation for the column of the identity matrix. So we have the transformation applied to the matrix X will be equal to A times the matrix X, and the matrix A is the transformation applied to all the column of the identity matrix TE1, TE2, and TE3. And then times X, of course. Now TE1 is 6, -3. Applied to E2, we have 2 and 0. Applied to E3, we have -2 and 1. If we want to, we multiply to X1. There are 3 columns, so X2 and X3. Yeah. Now if we actually want to multiply them out, we can just say it. We can put this in the matrix form or the vector form. So in the vector form, we have x1 times 6 and -3 plus x2, 2 and 0, plus x3, -2 and 1. So that is in the vector form. Or if we want to write in the matrix form, we can say 6x1 plus 2x2 minus 2x3, -3x1, x2, and plus x3. So that's all we have. So the matrix for the transformation is just whatever the transformation applied to the columns of the identity matrix. Later on we have a special name for it, but for now that's all we have. Right, next, find the standard matrix of the linear transformation T. Apply to R2, rotate the pawn about the origin to this counterclockwise rotation for the positive angle, right? So just gonna sketch here. Right. Of course, we can draw the unit circle. Just like what we did on the previous problem, we're going to write t of x, the transformation is equal to a matrix A times x. Now we're trying to find the matrix A. So matrix A will be given by the transformation of the column of the identity matrix. So first we have E1 will be the vector 1 and 0, or the point 0 and 1 are 1 and 0. So this is E1. You can write as a point or as a vector, that's the same way. E2 is 0 and 1. Now, the transformation. This is to the angle 7 pi over 4. 7 pi over 4 is, if we go from here, it will be this point. So this is 7 pi over 4, almost 2 pi. So it will transform, and this will be the image of the E1. So that pretty much, as you see, if this 7 pi over 4, this will be negative pi over 4. So this is the same thing. So this will transform into x will be cosine of just pi over negative pi over 4. And then y will be sine of negative pi over 4. Yeah, so y, x is cosine, y is sine. So cosine here we say is going to be positive, and sine will be negative. Square root of 2 over 2, and negative square root of 2 over 2. Alright. That's t of E1. T of E2, we go from this 7 pi over 4, so we're enough here. So this will be t of E2. So that's just pi over 4. So cosine pi over 4 and sine of pi over 4. That's just square root of 2 over 2 and square root of 2 over 2. So we found the transformation of the columns of the identity matrix. Now we just put them in a column. So A equal to TE1 square root of 2 over 2 negative square root of 2 over 2, and then TE2 square root of 2 over 2 and square root of 2 over 2. So that is the standard matrix for the linear transformation. Same thing. This will find the transformation. That first vertical shear that map E1 into E1 plus 5E2, but leave the vector E2 unchanged, and then the reflection of the result to the horizontal axis x1. So we're going to draw that out. Once again, what we have is the same thing. The transformation will equal to the standard matrix A times the vector x. and where A is the transformation applied to the column of the identity matrix. Times X. Right. 1, 2, 3, 4, 5. Right, so first E1 is this, and E2 is this point. Right, now the first one, it maps E1 into E1 plus 5E2. So what is E1 plus 5E2? So E1 plus 5E2 E1 5E2. So that gives us 1 and 5. So map from this one to x equal to 1, y equal to 5. So it's map E1 into E1 5E2. Yeah, so let's map that point to here. So we said TE1 is equal to 1 and 5, and leave E2 unchanged. So TE2 is equal to E2. Which is 0 and 1. So that's the first part. Next, then we reflect the result to the x-axis. So now we're going to have this point reflect to the horizontal axis. So that point will go down here, and we're going to have the vector x equal to 1, y equal to negative 5. But now the actual, let's see, this is not a t. Let's call this s. So the actual transformation will have two steps. First, it goes from E1 into that point, and then reflect back down here. So we should use the two operation like that. It's TE1, and we're going to the other one x. So now apply to E1, we're going to have 1 on original 1, and then E change to negative 5, because that reflects down, so it's 1 and negative 5. And after that, this point also reflect down, so this is actually T of E2 is equal to x equal to 0, y equal to negative 1. Right. So in this, the transformation T will have two actions. The first one, move point up and then reflect. So we have to write after two actions, the transformation to E1 of E1 is that, the transformation of E2 is that. So we put the column together. We have the matrix A equal to TE1 1 negative 5 and TE2 0 and negative 1. Right, next, determine whether the linear transformation T is 1 to 1 and whether it maps as specified here. So we have this transformation, whether the linear transformation is 1 to 1 and whether it maps onto R3 or R3. Right, so there are two concepts here. The first one is 1 to 1. The second one is onto. Right. So if it map onto, now just the review the concept here. So let's talk about one-to-one first. So if it is one-to-one, one-to-one meaning that we're going to map 1x to 1y. We cannot have the case where both of them go to the same one. This is not a one-to-one. Right? So in this case, we cannot have that. So meaning that if we have the system of equation, there have to be a unique solution. So we have to have unique solution. Which means the matrix matrix have to be no free variable. So that is a one-to-one function. Next, onto. So onto is where we have every point in the domain, some point in the domain, some point in the range. Pretty much every point in the range will have something mapped to it. So this is perfectly fine as long as all of the points in the range have the pre-image. Maybe more than one pre-image, still fine. So in this case, we just need to guarantee to have solution. Or just say solution exists. Maybe more than one. So if this is the case, what will be the equivalent to it? Now, if the solution exists, we cannot have the last column to be 0. I mean, let me just write it down. So if we have this scenario, the pivot on the last column, in that case there's no solution. We don't want that. So the point here is, if we do not want this situation, there's a way to say that if we have the pivot on every row, there will be no room for the pivot to be in the last column. Think about that. If we just ignore what we have on the last column, and when we do the operation here, if we have the pivot on every row, then the pivot cannot be in the last column, because the pivot can only be there. Of course, we might still have 0, 0 here, or some other numbers. But as long as we have the pivot on every row, particularly in the last row, then the pivot cannot be in the last column when we have the system of equation. So in this case, the equivalent condition to that is the pivot on every row. The pivot is on every row. So that's what we're looking for. So pretty much we just have the matrix A and then do the reduced row echelon form for it. We just need 3 by 3 because the last column could be anything, but that's all we need. 1, -2, 3, -1, 3, and -4. 2, -2, and -9. Right. So when we do that, we have the reduced row echelon form of the identity matrix. Right. Like that. Now, of course, if we have the augmented matrix. If we to solve for the equation of ax equal to b, so any vectors here, see, if we have ax equal to b and doing reduced row echelon form, we're going to have something here, and something there as the augmented matrix. So a augmented matrix like this, it doesn't matter what we have in this column. We have no free variable here, so no free variable. So the transformation is 1 to 1. Because there will be a unique solution. And then we do have the pivot on every row. So the pivot here, it cannot be here. Right? So pivots on every row. So T is on 2. We say T is R3 onto R3, but that's what we have. Right. Next, we just find A for A plus B. So this is very straightforward. For A plus B 4 times plus B so we multiply, divide, and then add or subtract. We don't have divide here, we just have the scalar multiplication actually. So 4 times everything inside, 12, 12, 8, and 4, 20. Zero, 4, -1, and 6. Then when add them together, it will be 12, 16, 7, and 26. Alright, so very straightforward. Of course, if we want to do that, just enter exactly as we see on the calculator. 2 by 2. 3 and 3, 2 and 5. 4 times that plus vector B. Zero, 4, -1, and 6. Right, so very straightforward. Right, now find 2 times A transpose minus B, so that should be easy. 2 times A transpose minus B. So first, the A transpose, we turn this row become column, and this row become column. So we turn it sideways. Row become column, row become column. So that is 2 times that, and then minus the matrix B. So multiplied inside be 2, 10, negative 4, 16, 8, and 0, minus 9, 1, 4, negative 2, 0, and 5. So 2 minus 9, minus 7, 10 minus 1, 9, negative 4, negative 8, 16 minus negative 2, 18, a minus 0 is 8, 0 minus 5 is negative 5. Right. Of course, we want to check with the calculator 2 times. This is the matrix 2 row with 3 column. Okay. 1, negative 2, and 4, 5, 8, and 0. Transpose. Again, second matrix, go to math, option 2. Right. Minus matrix B 3 by 2. Nine, 1, 4, negative 2, 0, and 5. So 7, 9, negative 8, 18, 8, negative 5. So that's good. Now find the product of A times B is defined as, if it is defined. Right. So we have A, the dimension is 2 row, 2 column. The matrix B, 2 row, 3 column. It is defined because the middle numbers are the same. So when we multiply, the product AB is going to be a 2 by 3, the outside numbers. Right. So AB that is negative 1 and 3, not negative 13. Right. So we know this is going to be a 2 by 3. So that's what we know it's going to be. Now, for each one, we're going to take the row of the first matrix, the column of the second matrix, multiply them, and then add on the product. So let's say this one on the first row, first column. So we use the first row, first column. Negative 1 times 0, and then plus 3 times 1. So that is 3. Right. And we can just pick any one. For example, if we find this one, this is on the first row and third column. So use the first row and then the third column. Negative 1 times 7 plus 3 times 2. So that gives us negative 7 plus 6 is negative 1. Of course, we can do that. Take a row on the first matrix and a column from the second matrix, multiply and add the product. So that 2 and negative 9, negative 2, negative 18, seven, and 12. Sorry. Of course, when we do that, make sure we put in the right entry. Sorry. Zero and 6. The negative 20 is here. Negative 20, negative 2, negative 18. And then 7 and 12, 19. Alright, of course, we're going to check with the calculator. Matrix 2 by 2 for A, negative 1, 3, 1, and 6 times the matrix two by 3, 0, negative 2, 7, 1, negative 3, and 2. Right. 3, negative 7, negative 1, 6, negative 20, and 19. So that's good. Now, I'll find the inverse for this matrix if it exists. Alright. So, for the inverse of a 2 by 2 matrix, there's a formula for it. It's 1 over AD minus BC. So, like cross multiply, subtract. And then the diagonal A and D interchange. B and C stay the same. However, we will change the sign. Right. So that's the inverse of a 2 by 2 matrix. So A inverse is equal to 1 over 0 times negative 4 minus 6 times negative 4. And then the matrix, the diagonal entry, swap places. The other entry negate or change the sign. Right. So that's 0 minus 20, that will be 24. Minus 6 and minus 4 to 24. And then negative 4, negative 6, 4 and 0. So multiply inside. Negative 4 over 24 reduced by 4, we have negative 1 over 6. Negative 6 over 24, negative 1 over 4. Over 24 is 1 over 6, and 0 divided by anything is 0. Right. So of course we can also use the calculator. And the inverse is that button. Convert this to fraction. So that's what we have. Right. Now show the system using the inverse that is given for the coefficient matrix. So if we rewrite this as the matrix equation, it will be in the form of ax times b, but where a is this coefficient matrix, and the variable x, y, z. equal to -4, 1, and -5. So here we have the matrix A times a vector x equal to a vector B. What we solve for the solution is multiply by A inverse on both sides. Inverse times a matrix is the identity matrix. Identity matrix times anything times identity matrix will be itself. So x equal to A inverse times B. So we have x, which is the vector x, y, z, equal to A inverse. So this is A, this is inverse. Times the matrix B. Right, we just multiply. Of course, you can do it by hand, but I just use a calculator here. Of course, if we have the calculator, just do reduce row echelon form. That's the most efficient way. Right, I'm just going to enter the inverse here. Or we enter the original matrix and then we hit the inverse button. That's the same way. Yeah, using reduced row echelon form is a more efficient way to solve things. Right, I check. Right. Well, I'm glad I check before I hit enter. Right. -1, 4, -1, 1, -5, 2, 0, 2, -1, -4, 1, -5. Right. So that is the solution. 13, -19, and 7. So x, y, z. -19 and 7. Or if we want to, we can write as upon x, y, z is 13, -19, and 7. Or if you really want to save space, you can also instead of write like this, we can say 13, -9, and 7 transpose. So there are a lot of ways to write this. We write like this if we don't want to write a column. That takes too much space. Just going to give it as a row and then we transpose it. Same way. Right. Next, find the matrix product A times B for the partition matrix. So pretty much we'll just take A times B. But this time it is in the block matrix. So in the block, 1 row, 2 column. Multiply this. Of course, we just put the matrix times together. There's no big deal here. but this will just demonstrate how do we write the blocks. Now this is in terms of a block, 2 by 1, 1 by 2, sorry, 1 row, 2 column. And in terms of blocks, this is a 2 by 2. So the middle number are the same. The product is going to be outside 1 by 2. So, of course, the product, we're not interested in the result. Just see how it will go. So first, check the row times the column. Alright, so in terms of a block, row first with the first, times column. So that's the first entry, row times column, and then row times column. Right, so this is one entry. Sorry, kind of ran out of space here. So that's the first entry in the matrix, and then we have 4, 0, 2, -1, 5, and 3. So first times first, and then plus row times column. So 1, -3, and 7. Sorry, I have space here. And then multiply by 3. So just going to put the 3 in front, will be perfectly fine. So this is going to be the result here. All of this is the first entry. That is the second. That is the first block. This is the second block. Like I said, I'm just going to keep in the block. The result, we just multiply the matrix together. That should be simple. I'm not going to write that out. Right. So next, we have this block. So A times B is 0, I, F times W, X, Y, Z. Right. So row times column. First row, first column. 0 times W is 0, plus I times 1. I mean I times Y. So first row, first column. Now first row, second column. 0 times X is 0. I times Z is IZ. And now we go to second row. I times W plus F times Y. And then I times X plus F times Z. Right. 0, I times Y, just Y. And this is just Z. I times W, just W. Plus FV, FY. And then I times X is X plus FZ. Yeah. So we just have that. Next, let me write the timestamp. What next is we use the LU factorization to solve for the system AX equal to B. So let's go with the theory first. AX equal to B. Now A is L times U times X equal to B. Now if we let UX equal to Y, then we have the system LY equal to B. Of course, from here we can solve for Y. Why we have that? We have UX equal to Y, and from here we can solve for X. Right. So there will be two steps, solve for Y and then solve for X. So first LY equal to B. So the first step is that. So LY, we're going to use by hand to do this one. We don't need a calculator. So L is this and U is that. Of course, lower and upper triangular. L is going to be 1, 0, 0. Try to write small because this might take a lot of space. Times Y. Y1, Y2, Y3 equal to B. Right, so the first one we have is just Y1 equal to 6. And the next equation, what we have is negative 2 Y1 plus Y2 equal to negative 3. There's no Y3 here. And then we can substitute the Y1 equal to 6 in here for Y1. So that gives us negative 2 times 6 plus Y2 equal to negative 3. So that is negative 12. So Y have to be equal to 9. Right, negative 12 move to the other side is 12 minus 3 is 9. And now we substitute this 2 into this last equation. Right. So substituting, we have 3 times 6 plus 4 times Y2, 9 plus Y2, Y3, we don't know, equal to 2. So 18 and 36. 18 and 36 are 54 plus Y2 plus Y3 equal to 2. So Y3 is minus 52. Right. So that is the first step. We have Y1, Y2, Y3. The second step is where we have UX equal to Y. U three, negative 1 and 2, 0, 2 and negative 1, 0, 0 and 4. So that is U times X equal to Y. We already know 6, 9 and negative 52. Right. So if this one we go forward from the top to the bottom, this one we go in reverse. We go in reverse from the bottom to the top. So this is backward substitution. That is forward substitution. So from here we have 4x3 equal to negative 52. So x3 is negative 13. So that's what we have for x3. Right. Now, from this second equation, what we have is 2x2 minus x3 equal to 9. And we substitute that into x3. So we will write 2 times x2, which we don't know, minus 13 minus negative 13 equal to 9. So that 13 moved to the other side is negative 13, so that is negative 4. So we have negative 2 for x2. And now we have x2 and x3. Now we can substitute into the first equation. 3x1 minus x2 plus 2x3 equal to 6. Right, now just substitute in the values. 3x1 minus x2 plus 2 times x3 equal to 6. So 3x1, 2, and negative 26. So that is 2 minus 26 plus 24 equal to 6. Subtract 24 over, we have negative 18, and so x1 is 3. 3x1 is negative 18, so x1 is negative 6. And negative 18 divided by 3. So we have x1 negative 6. If we do the math correctly, so this 2 minus 26 is minus 24. Move the 24 over, that will be 30 divided by 3, so it's 10. Sorry. So we have x1, x2, x3. 10, negative 2, and negative 13. Right. So this is how we use LU factorization to solve the system of equation. Right. So, and then if you ask how do we find the LU factorization, well, that is simple. Let's look at the next problem. Right, that's what we do. So we're going to turn this into a lower and upper triangular matrix. So what we do here is we just do row operation, reduce this into the echelon form. So first we will turn this into row echelon form. Actually, we'll have to do this by hand because we do need all the numbers. Right, so the only operation we use here is the row replacement, meaning that we will not swap in row, we will not multiply a row by any numbers. So we just have to keep it as is. So we're going to keep this pivot 2 and then turn the order to 0. To do that, what we need is we use the opposite of this number, which is negative 2. Times the pivot. And then we add and replace. To row 2. Now use the opposite. Times row 1. Times that. And then add and replace to row 3. So do that. I'm just going to do this by hand. The first row will stay the same. Right. 2 times negative 2 is negative 4. 4 0. Negative 2 times 4 is negative 8. 11 is 3. Negative 2 times 5 is negative 10. Plus 5 is negative 5. Negative 10 and 5 negative 5. Right, now row 3. 2 times negative 2 plus 4, so that's 0. Negative 2 times 4 is negative 8. Minus 1 is negative 9. Negative 2 times negative 5 is negative 10. Plus 24 is 14. Right, so the first column is done. Now next, the pivot here is good. Just need to turn this into 0, and then we will have a row echelon form. So we're going to take the opposite to this number, so we have negative. So we need to multiply 3 to it. This pivot is row 2. We add and replace to row 3. So the first 2 rows will stay the same. Right. 3 times 0, the pivot row 2. 3 times 0 is 0, plus 0 is 0. 3 times 3 is 9, minus 9 is 0. 3 times negative 5 is negative 15, minus 14 is negative 1. Right, so that's that. So what we have here is the pivot, and below the pivot entry at 0. So that's good. So this is the matrix U. So how do we find the matrix L? So the matrix L is going to be the lower matrix, where we have 1, on the diagonal. And then what we will have is, remember those numbers that we use to eliminate the entry in the first column, we're going to use opposite to that. So take this number, turn to opposite, and place that below the one in the first column. And then we'll take this opposite of that, replace in the second column. So that's what we have is LU. Of course, we can confirm by double check. We just take this times that. Sorry. Alpha zoom 3 by 3. L 1, 2, and 1, 2, negative 3, and 1. So that is the L matrix. Now times the U matrix. 2, 4, 5, 3, negative 5, and negative 1. Right. So we get back to A. So it's good. So we have A equal L times U, and L is this. And U is that. Yeah, so we just go ahead. Just go ahead and find the row echelon form, and in the process we find L as well. Right. Now we have another example here. But that looks familiar. Anyway, so we have the pivot here, and based on that we eliminate this to 0. So we're going to use the negative 2 times to the pivot row, and then add and replace to row 3. And then we use the opposite of negative, so negative 2 times 5 plus 10, that will be 0. So we use negative 2 again. And then add and replace, sorry, this is 2. And now row 3. Alright. So, first row stay the same. Negative 2 times 5 is negative 10 plus 10 is 0. Negative 2 times 2 is negative 4. Negative 4 plus 7 is 3. Negative 2 times 3 is negative 6. Plus 1 is negative 5. Right. 5 times negative 2, that's 0. Negative 2 times negative 2 is negative 4. Minus 5 minus 9. Negative 2 times 3 is negative 6. 20, that's 14. Right. So we're done with the first column. Now on the second column, this is the pivot. We just need this to turn to 0. So we're going to use a positive 3 times row 2. Add and replace to row 2. Add and replace to row 3, sorry. Right. So in that process, row 1 will stay the same. Row 2 will stay the same as well. And then the pivot is row 2. So 3 times 0 plus 0 is 0. 3 times 3 minus 9 is 0. 3 times negative 5, negative 15 plus 14 is negative 1. So that is the upper matrix. It is U, not the vector. We make that equal to matrix U. Right. Then the L matrix in the process, we just use the opposite to this number and opposite to this number. Of course we can check. We're going to check, by the way, this looks exactly like what we have on the previous problem. So we can check to verify that A is indeed equal to L times U, and L is 1 0 0 2 1 0 2 negative 3 and 1. times u, that. Right. Of course, we can just check with the calculator, but I don't think we need to. Right. I think this is a good stopping point. I will pick this up in the next video.